All right. Now we're going to do some techniques associated with our limits. We're going to compute them. We've seen the basics behind what we're doing with a limit. Now we're going to compute some of these limits. Before we get into all of that, we're going to have some limit laws. So let's talk about that first. So with our limit laws, we are going to assume that the limit as x approaches a of f of x and, oops, I put doesn't equal exist, and the limit as x approaches a of g of x exist. So we're just setting the stage basically. These are the values that we're going to be using in terms of limits, and so they exist. So I don't have to worry about that. Okay, the first one is going to be the sum. So if you have the limit as x approaches a of f of x plus g of x, then you can split that up. You can take the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Now the kicker honestly to this is the fact that they're both approaching a, so you're going to that same value. All right. Spoiler alert, we're writing all of these down, but we're going to shortcut through some of this. When we actually find these, we're going to shortcut through this. All right? Okay. So if I can do the sum, hey, lo and behold, we can also do the difference. And it's the exact same thing. You can think about this as taking the limit of my first term minus what happens whenever I take the limit, that's an arrow, the limit of my second term. We are not going to write all of this out. You're going to do this in your head, but I want to put these limit laws down on paper so that you know the concept behind the shortcuts that we are going to end up taking. All right? So that's what's happening here. All right, a constant multiple. So with your constant multiple, if I have the limit as x approaches a of c times that f of x, that's the same thing as taking the c out and just multiplying it by the limit of whatever I get from my function. All right? Okay. So a constant you multiply through there is just a constant you multiply through there. Product, same thing. If I'm going to take the limit as x approaches a of these two functions that are multiplied together, you can take the limit of each one and multiply that together. All right? So you're just taking the limit of each one and multiplying those together. Just the same as the sum, just the same as the difference. Oh, guess what we're going to do next? The quotient. Yeah, and spoiler alert, same thing. Now, what's the big deal whenever it comes to quotient? What's the one caveat that we can always have to account for? Yeah, 0 in the denominator, right? So you just have to put that in there. I'm taking the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, provided that the limit as x approaches a of g of x does not equal 0, right? So you always, anytime you have a rational, you always have to put that in there. We know that to be the case, but it's one of those, let's just make sure we understand it. If you do the power, it is the exact same thing. The limit as x approaches a of f of x to the n is equal to the limit as x approaches a of f of x to the n power. All right? The root is the same. This is the last one. Here's our root. the limit as x approaches a of f of x to the 1 over n that I'm looking at is equal to the limit as x approaches a of f of x to the 1 over n power. Now remember, we call this the root because you know this exponent up here is the same thing as power over root. And I'm just taking it to the first power, and then my root is n. It's just another way to put it as an exponent so that we can work with it a lot easier rather than showing it under the radical. But honestly, if you put it under the radical, then that would be the exact same thing. You could do the same thing as the nth root here of the limit as x approaches a of f of x. I mean, it's the same thing, right? Taking it to that exponent or putting it underneath the radical, right? Okay, so those are your limit laws.